So check footprint polygons tool has a new option, which is method check as list. And that gives you a traversable list of footprint polygons. So these footprint polygons are something that you may use in 3D building vectorization. And it's a good idea to do some validation on the footprint polygons if you're going to use those in 3D building vectorization. Because if we have a bad footprint polygon, then we end up with a bad 3D vector model. And this gives you a list that you can go through in an organized way. It's a traversable list. So if you want to check every footprint polygon, the list makes it straightforward and easy to go through every building, every footprint polygon. And you can make some changes. You can exclude polygons where you have no laser data. So you don't have any points classified as roof. That could be a classification issue, that the building classification has not classified hits on a roof at some spot. It can be a flaw in the laser data that we have a non-reflective roof and we didn't really get any points on the roof. Or it can be a situation where the footprint is from a different moment in time or is completely wrong, and simply there is no building in the laser data at that spot. But no matter what is the reason, if we don't have hits on the roof, we can't do a 3D building vector model. So I may choose to exclude all the polygons which don't have enough data. The coverage percentage is too small. I may have a situation where the footprint polygons are not that accurate. Perhaps they have been digitized based on an orthophoto, and in the orthophoto the roof is not in the right place, and so the polygon is not in the right place. And we can do adjustment on the angle, the rotation of the polygon, and we can shift the polygon to match the laser data better. We can do it automatically or we can do it manually. And we can fix corners to be exact 90-degree corners. So I have a design file which has footprint polygons on this level. So yellow elements. I have run building classification without using the footprints in that step. And I have run a macro which has, from my project, it has extracted all the building class points and all the high medium vegetation points next to a footprint polygon. And this is what it looks like. In some places, the footprint polygon doesn't look so convincing. I get the feeling that this is not the right rotation. I may have places where from the laser data, the software has found a building and I don't have a footprint polygon for it. I can have places where there is a footprint polygon and no laser data to show a roof. So I have all the medium vegetation, all the high vegetation points now in here. In the laser data, there's no building. I can have a situation where the footprint looks quite badly positioned compared to the laser data. And it's a good idea to check at some level this kind of differences so that the 3D vector models that are going to be generated are going to be better quality. I select all the polygons, or let me show, I don't think I've computed normal vectors. Nope, let's do that. So it's a good idea to compute normal vectors for this task. Not absolutely required, but I get a nicer display. I get more capabilities if normal vectors have been computed. And when the normal vectors are computed, I can look at normal coloring. Which helps me understand what is the shape of the roof. I can display things like this, or I can say that I want to use weight by class and check that my defined classes settings are such that high vegetation is a small weight, buildings is a bigger weight. So now the line weight of the point tells me if it was classified as vegetation or if it was classified as building by the software. And the color of the points tells me what is the direction of the slope if there is a sloped surface. If it's a flat roof building, then I see gray color. I'm going to select the polygons and I'm going to start check footprint polygons. I'm not using oblique images, so I choose none for the oblique view. Whether a footprint polygon has laser data for it, that computation is done with the principle that each laser point covers a circular area with 1 meter radius. So the right radius to use depends on your data density. And for the computation, we search data 5 meters around the footprint. And this takes a little bit of time. The software for every footprint polygon, it computes what percentage of the footprint is covered by laser data. So if we have a footprint polygon inside which there is no points classified as roof, that's a problem. If it's less than 50%, it's a problem. And the software computes the optimal rotation for all of those buildings where it finds that there's some sloped surfaces. So there's going to be some buildings where we don't have laser data. So this one, I can take the approach that I would draw a cross section from each to check if the vegetation laser points show a building roof. So I can have a situation where I have a building under tree canopy, and the automatic classification has not found the building roof. And then I can, with manual classification, I can classify it as building. Also, a building with this 50% type is questionable if we'll get a good vector model from it. %61 here. The footprint is not really matching the building. Here we have 0 and 0, so quite clearly I should not use these footprint polygons for doing 3D vector models. So as my first action, I might say that I want to mark missing data polygons. Anything which is less than 50%, I'll move the polygon, footprint polygon, to a different level and remove from the list. So I might later on take a separate look through those to see if there is classification that can give me building roof points. So now those have been moved to level 33, and those have been removed from the list. Then maybe I'll start going through all of this. I would sort by area so that the biggest ones are first. And this is often a nice way of going through because the automatic view setup is such that the software is simply centering a view. So it doesn't change the zoom factor, and with about the same size buildings, the same zoom factor works nicely. If I would jump from a very large building to a very small building, then I would have to zoom in, zoom out. And here the software is telling me that this footprint polygon is 99% covered by roof points. A feature here was not classified as building, and that's why it's not 100%, it's only 99. The software tells me that it would like to rotate this footprint polygon by 1.44 degrees. And that comes from the fact that the sloped surfaces and the normal vector direction of the sloped surfaces and the footprint polygon, they should normally match. So the software from the normal vector information of the points can come up with quite a reliable optimal rotation for the footprint. And it's giving a 75% reliability for the optimal angle. So I'm going to try auto rotate and just click. And that gives me the rotation that the software thinks is the best. And if I want, I can do an auto shift. And that gives me a position for the footprint vector, which the software thinks is the best. The angle is quite reliable. Whenever there's sloped surfaces, the angle is, in most cases, it's good, the automatic. The shift is not as reliable as the angle. So if I want, I can shift manually. So this is also possible. If I do it manually, I'm tempted to position the footprint polygon at the center of the point cloud. The automatic deduction uses a different principle. It tries to get the same elevation. So this edge and this edge, in most cases, they run at the same elevation on a building with a hip roof. Not always, but majority of cases. And the automatic position is based on that elevation principle. So we don't really know how much there is roof surface outside the walls. And just only looking at the area covered by the points is not a perfect principle. There is really no perfect principle, so there's only decent ones. But I'm happy with this one. I do have buttons here, approve and reject. Those are user definable. So I've defined that approve means that we move to level 26 and remove from list. Reject, we move to level 27 and remove from list. So you can have different actions, approve, reject, classify, and move footprint polygons to different levels when you click on that. I'm going to move to the next one. There's a minimal angle change and a little bigger automatic shift. Here I can't do the auto rotate. The angle is so minimal. And the shift is 0 as well. So there's nothing automatic that I do, and this all looks good. This one looks like its rotation really needs to be fixed, and I do the automatic shift. Here again, the rotation is not good. I do the automatic. I look at the automatic shift. I'm not sure if this is better or what is right. There's clearly the roofs are larger than the footprint, larger than the walls, and it is quite hard to say what is the right position. If there is an auto rotation to do, I would generally do it. This one looks questionable. If the footprint polygon is usable or completely useless, maybe I would decide here that okay, I'll do the auto thing and let it be that way. But this is what I would do. I would often use the auto shift, auto rotate, sometimes use the auto shift. Here, what is nice is that I see the corner aligning with the intersection of these two planar surfaces. So this here looks good. Here we have something which is not 90-degree angles, does not match the laser data very well. There is a fixed corners, which fixes corners to be 90 degrees. So that's something you can do. Here I might do a manual shift. I don't really know what is the right place, but the original looked quite awful. I'll do the auto rotate. No shift that is needed. Small auto rotate. Small shift. So the shift brings this elevation and this elevation to be matching better. And this is the work that I would I would do. And it was all about modifying vectors, accepting the good ones for use in 3D building vectorization, or rejecting the bad ones, so that those are not going to be used. Check footprint polygons can also be used with oblique images. So when we look at the airborne laser data, we don't see the walls. We at the end of the day, we don't know where the walls are. If we look at an oblique image, looking at the building, then we can really see where the walls are, or if there is a wall. And the way the walls are displayed against an oblique image is that the software shows straight line segments at the ground level connecting visible corners, and it displays a vertical line for each visible corner. So the ground level of the footprint is not always visible, and it's not always easily understandable. So the vertical lines help me understand what is the position of the footprint corners compared with the image. And this kind of viewing, I don't use so much to modify the positions. I use this more to understand when a footprint polygon is usable and when it's not usable, when we need to include something into the footprint polygon to get all the walls that need to be in the 3D building vector model. So I look at, is the footprint in the right place? And does the footprint include all the places where we have a wall in the building? So we are going to have roofs which have no walls. We are going to have places where we have a wall at a higher elevation, but not at the ground level. And there's going to be all kinds of cases where there's something of a discrepancy between the footprint polygon and the real walls, or the walls that I would like to have for 3D building vector creation.